So continuing chapter 15, what we're going to talk about here is something called Q, which is a reaction quotient. And what is its relationship to K? When does it equal K? So Q, okay, is any point in the equilibrium reaction. So K is defined as at equilibrium, what are those concentrations of products and reactants? Q is a way for us to figure out where are you in the process. So I think of it more as a snapshot of where you are, maybe an instantaneous rate kind of idea. So Q is still going to be products of a reactants. You could have a QC, you could have a QP. So Q is the same as K. It's just how you're looking at it in terms of a constant compared to where you are in the equilibrium process. So we need to talk about its relationship to K, okay? So what if it's less than K? What if it's greater than K? What if it's equal to K? Well, if it's equal to K, you're at equilibrium, okay? So if you have the exact same amount of product and reactant, when you do the math, it equals your K, you know you're at equilibrium. Well, what if the Q is less than K? Okay, so what that's saying is I need to bump it up some more. I need to make more product. So that means I'm going to shift it towards the right and make more product to get it towards equilibrium. Because obviously I'm not there yet, okay, if I'm below K. If I'm above K, it might have been I put too much in there in terms of what I was starting with. And so that means it's going to shift to the left and make more reactant in order for that K to be where it's supposed to be. Now realize K is a constant, so it's not going to change, but the Q can't change. So please write down page 647, and I'm going to show you the graphic here in a second. So this is found on, like I said, page 647 in your book, and I think it's a nice figure for you to kind of understand the relationship of Q and K. So I think the easiest one to understand is this top one. So Q is less than K, so that means it needs to make up and get to that point of K, so that means the reaction proceeds to form more product. If Q is equal to K, then of course you're right at equilibrium, you're right where you're supposed to be. And if somehow you're above the amount that you need to have, so the Q is greater than the K, the reaction is going to proceed to form more reactants. Because again, it's always products over reactants, so that's going to be how you differentiate it. So go down in your notes and let's do a problem so you can kind of see how this works. So here is my equilibrium, and I'm given a Kp, they all are gases. And if the pressures are given here, find the direction of the reaction. So there's a couple things that you want to look at. It's asking for direction of the reaction. So that should clue you in that you're probably looking at some kind of Q. The other thing that should clue you in is the fact that I have concentrations or pressures of each species. So we're talking the reactants and the products. Typically, if you're finding a K, something is starting at 0, typically. Okay, so that's going to be how you distinguish that you really have a Q here. So I'm going to take my product, the PClO5 is 0.025 atmospheres. On the bottom here, PCl, that's 1 atmosphere, and Cl2 is 5 atmospheres. So this comes out to be about 5 times 10 to the negative third. All right, so what is that compared to our constant, okay? So 5 times 10 to the negative third compared to 5.4 times 10 to the negative third. The Q that I calculated is less than K, okay? So what's the direction of the reaction? It's going to the right. It's going to make more product because it has a deficit. It needs more product, okay? So let's take that and apply it to kind of an ice table, okay? So I want to find the equilibrium pressures of each because I'm not at equilibrium. So again, I'm going to do a quick ice table. So this is 1 atmospheres, this is 5 atmospheres, but this is different. This does have a pressure at for the product, okay? So how do I do my X's here, okay? Traditionally, We have something that is starting at 0. So how are we going to figure this out? Well, because I am making more product, it's going towards the right. That means this side, I have to make more product. So this side has to be the positive side. This side has to be the negative. So for these types of problems, you have to look at what your Q is in order to figure out which direction you're going. So this is 1 minus x. This is 5 minus x. This is 0.025 plus x. So those are your concentrations, your pressures at equilibrium. Well, I got nothing at equilibrium, but I do have a K value of 5.4 times 10 to the negative third. So I could use that to do some of the calculations. So what's my product? 0.025 plus x. On the bottom is 1 minus x and 5 minus x. All right. So some of you math-minded people might understand at this point, I have some kind of quadratic, okay? Well, we are not going to do the quadratic, and some of you have problems when I do this. All right, we are going to consider x to be very small because I am 5 times 10 to the negative third versus 5.4 times 10 to the negative third. I am not that far away from equilibrium. So I'm going to cancel out the x's on the bottom. Okay, I can't cancel all the x's, otherwise I can't solve for x. Realize that if I have 1 atmosphere or 5 atmosphere, this small of a number is not going to be that significant. So I will explain how we could do this. And again, some of you are really going to fight me on this one. But essentially, I have 5 on the bottom, so I'm going to bring it over here. So this is 2.7 times 10 to the negative second is equal to 0.025 plus x. So x is equal to 0.002, which again, if I subtract that from 1, it is relatively small. So what's the amount, or what is the equilibrium pressures? They are pretty much approximately 1 atmosphere, 5 atmospheres, and then this is the only one that you can write down or add the 0.0022 to is 0.027 atmospheres. So again, we're going to see some of these types of problems, and sometimes it's going to be very easy to solve for, but for right now, we're going to say we're going to cancel out that x. So getting into a later topic in our discussion, what effect does temperature have on equilibrium? Okay, so what do we know about K and temperature? Okay, so think back to kinetics, all right? We had the Arrhenius equation, and we do have a relationship. So temperature will be affected, K is only affected by temperature, but K is a constant otherwise, okay? So I need to know in this equilibrium, where is the heat, okay? Because if it is endo versus exo, okay, my K is going to get bigger or smaller depending upon if I have products or reactants more dominant in that equilibrium. So equilibrium temperature will affect the K, okay? The K will change if I change the temperature, okay? But that's the only thing that's going to change the K, okay, is temperature. All right, so we'll come back to endo, exo, and discuss that further.